Hi guys, in this lecture we're going to be talking about advanced feature detection. Okay, so in previous lectures we introduced feature detection and extraction, but we mainly focus on the common geometric shapes like lines and circles. Even blobs assume that there's a contiguous grouping of similar pixels. In this lecture, it mainly builds on the results by looking for more complex objects. Most of the detection is performed by searching for a template of a known form in a larger image. In this lecture, we will also provide an overview of optical flow, which attempts to identify objects that change between two frames or sequential frames. If we look at the scope, we're going to be talking about template matching, tracking objects that move, or basically using optical flow, barcode scanning for one-dimensional and or two-dimensional barcodes, optical character recognition, feature correspondence or key point matching, and then finding key points, which is more robust form of template matching. Okay, so let's look at what template matching is and what the goals are. Well, the basic goal is to learn how to use template matching functions so we can search for matches between an image batch and an input image. So what is template matching? Well, template matching is a technique for finding areas in an image that match or basically are similar to the template image, which is the batch. There's two generic methods of template matching. If you look at the algorithms, there's the square difference matching method and the correlation matching method. So one of them uses the squared differences. So the perfect match will be 0 and bad matches will be large. Or we can use the correlation matching methods. The generic one that's used is the normalized cross correlation. And this method basically matches the image so that a perfect match will be large and bad matches will be 0. Now, how does template matching work? Well, we basically need two primary components. One is the source image and the other is the template image. Source image is basically the image in which we expect to find a match to the template image. And the template image is the patch image which will be compared to the template image. And our goal is to detect the highest matching area. If we take our template image and this is our source image, we scan it right through the image and then we detect that the highest correlation is in this area. As mentioned before, to identify the matching area, we have to compare the template image against the source image by sliding it. By sliding, we mean moving the patch one pixel at a time, left to right, up to down. At each location, the metric is calculated, so it represents how good or how bad the match is at that location, or basically, how similar is that patch to that particular area of the source image. A perfect example of using template matching is to find Waldo. I'm sure most of you have heard of the game called Where's Waldo? So we have Waldo over here and we have to try and search for him within this image. Now it's very difficult to find it just by looking at it. It will take a lot of time. Now if we have a template image, we can basically scan the image and then find the highest correlation area of where Wally will be. So as mentioned, this algorithm works by searching for instances where the bitmap template, a small image of the object to be found, can be found within a larger image. So for example, if you're trying to create a vision system to play Where's Waldo, the template image would be the picture of Waldo. And to match the most important features, his face, the Waldo template would be cropped to right around his head and to include minimal amount of the background. Now the template of his whole body would only match instances where his whole body was visible and positioned exactly the same. The other component in template matching is the image to be searched. Here is another example, which is the checker beads. Now, the template matching feature works by creating a template first and then calling the template matching function, which can be found in Vision Assistant and on the image object to be searched. And then we pass a parameter of the template of the object to be found. So another app that we will be building, we'll be using template matching to find how many beads there are, or we can say how many black beads there are, or how many white pieces there are, or red and black. Or we can use it for chess pieces as well. Now we can also use template matching for object tracking. The National Instruments Vision Development module also introduces a new algorithm for object tracking, which tracks the location of an object over a sequence of images to determine how it is moving relative to the other objects in the image. The object tracking has many uses in applications areas such as security and surveillance. So in the surveillance industry, objects of interest such as people and vehicles can be tracked. Object tracking can be used for detecting trespassing or observing anomalies like unattended baggage. Traffic management. The flow of traffic can be analyzed and collisions detected. In medicine, cells can be tracked in medical images. In industry, defective items can be detected and tracked. In robotics and navigation, robots can follow a trajectory of an object. Robotic assistants can maneuver in a factory, depalletizing objects. In human-computer interaction, or HCIs, users can be tracked in a gaming environment, such as a Kinect. In object modeling, the object can be tracked from multiple perspectives and can be used to create a partial 3D model of the object. And finally, in biomechanics, tracking body parts to interpret gestures or movements. This can be used for medical analysis or for robot modeling. Okay, so this really good algorithm does come with its limitations. So this approach supports searching for a wide variety of different objects, but the image being searched always needs to be larger than the template image for there to be a match. The size of the object in the template must equal the size it is in the image. Lighting conditions can also have an impact because the image brightness or reflection on specular objects can stop a match from being found. As a result, the matching works best when it is used in an extremely controlled environment. More critical issues, there is sensitivity to changes in size and rotation. Sensitivity to pattern distortion, for example, if you have a varying viewing angle, if you change the viewing angle of a camera. Also, there's noisy matches. Unexpected configurations may occur that produce high matching values. And another problem is that it has a heavy computational load.